So now I will start with presenting my dissertation entitled Towards Intelligent Robotic Systems, Unifying Model-Based Optimization and Machine Learning for Planning, Control, and Estimation. So my primary objective in my dissertation is to find methods that can make robots completely autonomous. So that's ultimately my passion. And this is done through developing end-to-end frameworks that can consider the interplay of planning, controls, and estimation simultaneously. My solution to develop these kinds of a framework is to do a more hybrid approach to accounting for robustness and predictability using model-based optimization techniques, but still considering the non-linearities that might exist and are difficult to model by using learning-based approaches. The presentation outline will be the following, and then I'll conclude with my current work and also the future work that I'll be doing as a postdoc at Merle. So first, I'll discuss my work in the active SLAM field, and I'll show a motion planning framework for multi-agent teams. So this is something I presented in my oral exam. And then in terms of some new works, I'll demonstrate an auto-calibration techniques of parameters, but I'll apply it on not only controllers, but also planners for legged robots doing online operation. And then finally, I'll present a state estimation system for legged robots, and it will incorporate both machine learning and then also model-based techniques, which is sort of this theme in my dissertation. So I'll start with active SLAM. So SLAM stands for simultaneous localization and mapping. So in other words, we want to estimate the state of the robot using features of the environment or the map. And then the active part of this framework is when we also consider planning in as well as the localization and mapping part. So there's a lot of different approaches to this kind of active SLAM problem. My approach is to use a model predictive controller for online path planning. And this planner will be informed by an object detection system and also an RNN. And then this RNN is going to be trained on SLAM algorithms and estimations for obstacle avoidance. So this led to, and I used this kind of framework for the following work called SABER, Data-Driven Motion Planner for Heterogeneous Robots. Ultimately, it consists of a stochastic MPC for avoiding the obstacles. So this is used for local motion planning to reach some kind of target position. It's stochastic because we'll be considering chance constraints for the obstacle avoidance part. So here present the MPC formulation, which consists of your typical objective function, which is to track some kind of reference trajectory as shown in equation 1. We have some shooting constraints shown in equation 2, and then we apply state and control limits in equation 4. But then the obstacle avoidance part is based on these kinds of chance constraints. Now, if you want to use equation 5 in your optimization solver, you're going to, the typical technique is to convert this constraint into a linear deterministic constraint. So I'll discuss this one here. So essentially, this is represented by equation 7 and 8. I do leave out some of the details of how these equations are derived, or essentially going from 6 to 7 and 8. But you can find those details in Blackmore's journal paper. But to provide kind of a simple explanation of these chance constraints, for those who are not familiar with them, let's assume that, for example, C is equal to 0, and then we make this into a quality constraint. Then we'd have something like AX equals B, which is simply a line constraint, where A vector is normal to this line. So then we create a line constraint to essentially represent this kind of obstacle. So these are represented by the black lines. So then the X variable will represent all the points that are on the line. Now, if we add the C term back in, we create this kind of offset, which is represented by the red line, so essentially shifting it. And then if you make it an equality constraint, now X represents all the points on the red line and also all the points in the direction of the vector A. Now, the significance of the value of C is that it's a function of the covariance matrix, which contain the uncertainty, and also by a user-defined variable called delta, which signifies the probability of constraint violation that we allow. So essentially, it's a soft constraint. So ultimately, you can think of C as defining a boundary of safety around the obstacle to ensure collision does not occur by some probability defined by delta. And we can also technically consider circular obstacle by adding the C term to the radius of the obstacle, and then that also signifies some kind of boundary around the obstacle. So we present this in this kind of toy example. So we show the SMPC running on 2 of the robots, trying to avoid these circular and then also these convex polyhedral obstacles. We also show a more complicated gazebo simulation where we have a turtle bot trying to reach its goal state using the SMPC, and then also for a drone to reach its goal state. And then after this, I will show also show a more dynamic example shown here. So it's going a little bit faster with more obstacles, and we can also handle this kind of environment as well. So that's essentially the SMPC controller for this framework. In this case, we're going to have a robot team. So each robot will have its own stochastic MPC. We consider the dynamics of each of these individual robots. So we have a turtle bot and a drone. Each one will have different kind of sensor configurations. So for the turtle bot, we have a LiDAR. So we're going to use particle filter SLAM for estimation. And then for the drone, we have an RGB camera and IMU. So we'll use visual inertial odometry SLAM. These SLAM algorithms are going to send their outputs as an input to a recurrent neural network. And the goal of the recurrent neural network is to predict the future state uncertainty covariances for the future time step. And then the current uncertainty we can get directly from the SLAM algorithm. Now, the purpose of the RNN is, again, like I said, provide a quick prediction of future state uncertainty covariances. You can do this using your typical filter equations, like a common filter or extended common filter. But if you use those kinds of equations, you essentially, you're assuming that the uncertainty will keep increasing. Then you get the measurement update, and then you get a more realistic value of these uncertainty covariances. So the RNN idea is very simple. We just try to model the behavior of a filter at those measurements updates. So then in the testing phase, you get your measurement updated time step t, and then you can predict what the measurement, what the covariance uncertainty matrix will look like in future time steps without necessarily having those measurements at that point. You can also think of it inversely, where you're trying to predict what the measurements might look like for future time steps. Now, the reason why this can be important is because MPC will solve an optimization problem for a prediction horizon. So of course, if you have a more realistic value of uncertainty rather than assuming a very conservative approach where these uncertainty covariances keep increasing, then technically you'll have a more optimal control solution. So in terms of training this kind of RNN, it's quite simple. You have a SLAM algorithm. In this case, let's say we're using Xevo. Xevo takes as input IMU data and RGB images, and then Xevo will give us the feature locations of the map. So these are positions, and then also the state of the robot. And it also gives us the covariance matrix or uncertainty from the SLAM output. So the RNN essentially tries to relate the inputs, which are the feature location and robot position, and then we try to predict the output of the robot covariance matrix. So this is sort of the data collection process using the particle filter SLAM, and then for the VRO SLAM. And then we show the loss decreasing. And then just to validate that what we're doing makes sense, of course, in feature-poor environments, you're going to have higher uncertainty, whereas in feature-rich environments, we'll have lower uncertainty. So this is true for both of these SLAM algorithms, as we would expect. So now we have multiple robots, each one trying to estimate its state estimate and also the covariance matrix. And then we can fuse this data using a distributed common filter. This is a very sort of basic technique that you can use to fuse multiple data from uncertainty data. And then this can be used, and the importance of these uncertainty covariances is because they use as input to the obstacle chance constraints. So they will directly affect the ability of these robots to avoid the obstacle safely. So here to show visually how the covariance matrices will decrease when multiple robots in a communication range. So heuristically, I basically say the distributed common filter is activated when the robots are within a certain range. Now with this kind of setup, we might still have some local minima issues. Again, the MPC has a limited prediction horizon. So for a very large obstacle like this one, you kind of will run into a local minima issue. So at that point, we do need some global path planning. Now, there's many different ways to do it. The way I chose, or the method I chose, is to use a simple DQN reinforcement learning. The states are very simple. It's essentially the relative distances between the robot and the other robot, and also the robot with the other obstacles in the environment. The action space is also is assuming a simple grid space environment, and then you get rewards for getting to a goal position, being near other robots, and then it gets a penalty for collisions. Now, there's a bit of a caveat when you use this kind of DQN. Essentially, it really only works up to 4 robots because the action space will exponentially increase. So that's something to keep in mind if you want to use this kind of method. So that's a limitation. In our case, we just consider 2 robots, so it's not. It worked at least for our application. So here, just show the training process. Again, a very simple grid space environment with multiple robots trying to get to the goal position. Then we add this DQN to this framework, which does the global planning. It sends sort of this waypoint or next target position to the SMPC, and it's the SMPC that ultimately considers the dynamics of the robot and does the obstacle avoidance part. So then with the DQN, we can avoid the local minima issue. And then I think I wanted to show the video afterwards. So this is one example where it's just avoiding that one big obstacle, and then here's for multiple obstacles as well. And then we also applied this kind of MPC RNN system to legged robots. So here I show the data collection now with a camera on a legged robot system. And then we showed the obstacle avoidance for the Alfred robot. So that's one of the quadruped robots we have in our lab in both simulation and also in hardware. To kind of more visually demonstrate the importance of an RNN, let's say you have a baseline MPC. In this case, uncertainty is not considered, and localization is assumed perfect, but the simulator does have some uncertainties. So in that case, you can easily run into a collision. You can do something more naive where the uncertainty is sort of static and inflated, so large collision boundaries. So in that case, you will be able to avoid the obstacle, but it's a safe and slow approach. And then with the RNN, which is a bit more dynamic in how these uncertainties are represented, we can say it's a safe and also faster approach. So this concludes the active SLAM portion of the presentation. But now, so as I mentioned, so far we showed one example of an end-to-end system, but you might also notice that there's a bit of an issue here in the sense that we have all these different modules, and technically, we have a comment filter, an MPC, an RNN. All of these have parameters that you need to constantly tune and retune depending if we change environments as well. So this is, of course, very challenging. So this made me look into auto-calibration techniques. And essentially, the way this auto-calibration can be done is through an unscented comment filter. You can find more detail in the paper I showed below, but we will show it for the first time on also legged robot system and also for calibrating planners and not just controllers. Now, to kind of preface, again, this auto-tuning is really just an unscented comment filter with the usual sigma point prediction update steps. The only thing you need to change your mind on this is what we define as our states and what we define as our measurements. So to use this kind of system, we start with the states of a UPF. In this case, instead of calling them states, we'll call them as control parameters, but the equations are identical. We then use the common gain, which is calculated as a result of the prediction step to find the updated control parameters. And essentially, you can think of this term as a cost function where y is your reference value, so what you want to achieve, and then the h is the evaluation function defined by the user, which is typically also a function of your measurements and also a dynamic model. So here I show one of the works called Auto-Tuning of Control and Online Trajectory Planner for legged robots. So this was something I presented at IROS. So the methods are going to be the following. First, we assume access to at least some initial reference body and footstep trajectory. This trajectory may be calculated using either complex trajectory optimization methods, or in our case, we just use very simple methods using Euler discretization to propagate some center of mass velocity, and then cycloidal functions to provide the footsteps. And then this reference trajectory is going to be updated using our auto-tuning method. For example, we may use the swing height of each leg as a control parameter, where the swing height of each leg is calibrated so we can achieve a desired swing height based on the feedback from the state estimation system. Now, in addition of tuning the reference trajectory, we will also tune the controllers. So our legged robot has 2 controllers. One is a MPC stance controller when the foot is in contact with the ground to follow some center of mass base reference trajectory, and also consists of a PD swing controller when the foot is not in contact, so in swing state. And then both the MPC and the PD controller have parameters that we can tune or calibrate during operation. So I'll discuss more detail in the next few slides about that. And then the controller will provide you output joint torques, which are sent to the robot directly. In our case, we're going to use the A1 unitary robot to do this. And then this is how the framework will look like. I will now show the training objectives that we consider in this work. So first, we look at tuning the costs of the MPC stance controller, which are going to, again, produce optimal forces at the foot to stabilize the robot's base. Now, the auto-tuner will require a dynamic model, and we're going to use the following state space model that you see here. I won't get into much detail on this model. It's essentially a single rigid body model that at least people in Lego robots are going to be very familiar with. And the parameters that we're going to calibrate are going to be the Q and R cost matrices of this stance controller. And then the overall training objective is that we want to calibrate those weights so that the predicted center of mass trajectory given by H is going to be equal to your desired reference. So essentially making sure or provide better tracking of your reference trajectory. For the swing controller, we're going to use the following PD controller that has both a feedback and feed forward terms, as you see here. The dynamic model in this case is going to be simply based on the equation of motion, which can determine the joint positions and velocity. And of course, through the Jacobian and forward kinematics, we can also retrieve the task space, footstep position and footstep velocities. And then in this case, the control parameters are going to be the KP and KD gains of the swing controller. And then as before, the training objective is we want to follow a desired reference trajectory as well as we can. Now, the sort of contribution here is that we actually use this kind of system to also calibrate the reference trajectory as well, so not just controllers. In our case, our trajectory generation is simple, and we just use, again, as I mentioned before, the desired velocity in combination of cycloidal functions to generate both the center of mass and footstep trajectories for n number of time steps. We use the same dynamic model as for the swing controller, since the joint acceleration provided predicted footstep position and velocity through, again, the kinematic relationship. And in this case, the control parameters for the reference trajectory is going to be the step clearance or apex height of the footstep during its trajectory. And then the second parameter that we tune is the velocity of the center of mass, specifically the forward progress or forward velocity. Now we're going to use actually several training objectives to do this kind of, or to optimize this training objective. So one of the first two are going to be obvious, right? We first want to predict, or want the predicted velocity given by HV to match a desired velocity. And second, we want the predicted step clearance given by HC to match the estimated height of the trajectory. Now, in addition, we can actually consider really any kind of training objectives we want. For example, we can make sure that the chosen parameters for the step height and forward velocity try to minimize some kind of slippage by essentially reformulating or formulating essentially the friction cone constraints in this way, for example. And of course, maybe we also want to minimize energy consumption. Again, this can be calculated simply by joint velocity times the joint torque. And then we set the desired y value to 0, which means we want to minimize the energy consumption. So ultimately, we combine all of these training objectives all at once to essentially calibrate the step height and the forward velocity that best minimizes all these objectives that I just laid out. So here we show our results in calibrating only the MPC and PD swing controllers. We do start with bad initial gains and then let the auto-tuner calibrate these gains during operation. So in the left video, we use the auto-tuner to calibrate, we use the auto-tuning, while in the right video, we do not use any auto-tuning. So as you can see, after a while with the auto-tuning, the robot can, essentially keep walking forever, while without it, eventually the robot becomes unstable and then quickly falls. Here we then also show the results when calibrating the reference trajectory directly and consider as training objectives following some desired walking speeds, increasing foot clearance while simultaneously minimizing foot slippage and energy consumption. So we can see that we have a desired velocity of a certain amount, and then eventually we'll keep increasing through the auto-tuning until it reaches its desired value. So we started with a low step height, but we wanted a step height of about 0.115. And as you can see at the end, it sort of reaches that value. And then we use and then once we tuned our robot, we can apply it now to rough terrain. So here we show it stepping over some planks and then also walking over beams. So essentially just to show that, the gains that we calibrated were decent and allowed for this kind of locomotion. And one thing to also say, there's absolutely no vision in this. So the robot is just walking blind, trying to go forward as best as I can. And then here we show also some recovery against falling. Again, we don't consider vision, or it doesn't really know that the stairs coming in front. It's just the NPC really trying to essentially save the robot from falling. And we can also show like a jumping gate. We also were able to show a little bit more kind of rough terrain locomotion here, going over this kind of more difficult terrain. And then I also showed other application of auto tuning as well. Again, I won't spend much time here because this is something I did present at the oral exam, but we use it for tuning the gains of the admittance controller for tracking reference wrench trajectories. So here's one where we showed in a previous paper where we received a wrench trajectory and then the admittance controller tries to track it as best as it can for robotic climbing. And then in that work, we showed that without tracking, the robot would slip, and then with tracking, the robot did not slip, just to show that we were able to tune our trajectories for our admittance controller very well. And then here we showed our ability to track wrench profiles for multiple components of wrench using the admittance controller. And then we also show to kind of show what it might look like when we have no or bad gains during the pull-up motion. So you can see that it looks very unstable, and then after tuning, we show something much more stable. And then lastly, we also showed this auto-tuning aspect on also real-to-sim application, where we tried to learn the residual error between the simulation and the real robot. So we were able to do that. And again, the advantage of this auto-tuning method, unlike maybe using neural networks or something like that, is that we only need a few seconds of training in order to learn the residual error, and you can apply it directly on the real robot. So that's sort of the advantage of this kind of UPF system. All right, so now that concludes the auto-calibration part. Now I'll go into state estimation. So ultimately, we showed different kind of methods, and includes controls, model-based methods, and even for RL algorithms. And in most cases, ideally, you still want to have a very good state estimation system, because that will just make it much easier, for example, for RL methods to apply it to the real robot. And of course, model-based methods are also going to be very dependent on how well your state estimation system is going to be. So this led me into developing a work for state estimation of legged robots, because typically state estimation for legged robots is challenging. So there's a lot of work that can be done in this field. So it's called OptiState, state estimation of legged robots using gated networks with transformer-based vision and Kalman filtering. It's something that I presented at ICRA last month. So to first try the motivation of this work, first estimation for legged robots is difficult, as I mentioned, and it's because we have a lot of dynamic motion. So this can cause motion blur for the camera, so that makes vision data unreliable. And because these robots are constantly making and breaking contact, you often have slipping. So even joint encoder information cannot always be very accurate in some cases. So the solution is to employ a hybrid approach. Again, has been my theme in a lot of my works, which consists of model-based Kalman filtering, which means that we can employ some amount of domain knowledge here, optimization for improved robustness, and then we'll use learning methods to correct also for the nonlinear errors that we really cannot avoid, especially on real robots. So we're going to have sensor measurements using a depth camera, IMU, and joint encoders. These joint encoders are going to be used as input to our forward kinematics. And then with these forward kinematics, we can estimate already the robot's trunk velocity by taking the average velocity generated by each footstep in contact with the ground, including the contribution of angular velocity of the trunk on the footstep position. And then, of course, the height of the robot we can estimate by simply looking at the distance between the body of the robot and the footstep location that is currently in contact with the ground. So these measurements are used as input to the Kalman filter. In this case, we're going to use a very simple Kalman filter And then, of course, we do need a dynamic model. Now we do something a little bit interesting in terms of how we generate this dynamic model. Essentially, these equations again show the single rigid body model that I've shown in the past. And then these are essentially the equations, and you can use convex model predictive control to essentially calculate the ground reaction forces, which, as I mentioned before, is about trying to track some kind of reference center of mass trajectories. So again, this is actually a control output to calculate F. So again, if your robot already has this MPC, then it's nice because you can simply reuse those ground reaction forces for the dynamic model of the common filter. Now, of course, if you don't have an MPC, that's still fine. It's a very simple optimization. It doesn't take much computation time, so you can add this optimization to your framework, and it will help with the state estimation. So then ultimately the output of the common filter along with other variables shown here, I then send this input to the GRU. Again, the common filter will provide already an initial estimate of the robot state, and then we send that to the GRU. In addition, another input of the GRU is going to be the latent space of a depth image, and we get this latent space by using a vision transformer for autoencoding. So I'll provide a little bit more detail. So this is, again, a very typical autoencoder transformer method. We input the depth images, we try to randomize a little bit, and then the goal of this transformer is to try and reconstruct the depth image from a latent space. But all what we care about here is really the output of the encoder, because the encoder output has this latent space representation, and it's those latent space representation that we send down to the GRU. The output of the GRU is going to be a refined state of the robot. So it uses input of the common filter and then tries to refine that state. So the outputs are going to be essentially two outputs. So one will be X bar, which essentially which is the state of the robot, and then we need some ground truth here, which we get from the motion capture system. In addition to estimating the state of the robot, we also try to predict what the error between the GRU's own state output is and the motion capture system. So to provide sort of the simple explanation of this, during training, the GRU will predict some output, X bar. We subtract it from the motion capture or ground truth data to get E, and it's essentially that E that we're trying to also learn simultaneously during this training procedure. So in that sense, we can get not only the state output, but also some error about this state. And this just shows the loss function for the autoencoder and then the GRU. And then this will define our overall framework. So to provide more of an overview, we have a high-level planner that sends its trajectory to a controller, which tries to track this trajectory. And then the output of the controller will, in a symbiotic relationship with this state estimator, send those to the state estimator. Then, of course, the current state is then sent to the controller. So here we show the autoencoder after training. So the output image is, again, the reconstructed depth image after being encoded into a latent space. And then we show the data collection of the GRU. So we have a depth camera that's located in front of the robot, IMU data, and then motion capture for the ground truth. And then we use a visual inertial odometry SLAM as our baseline. So here we show the robot walking on flat terrain. And then we also show on the robot on slippery terrain by putting essentially socks on the robot's feet. And then occasionally we also sort of pull and push on the robot just to induce more, I guess, more noise into our data set. And then we also show an inclined terrain, so we can generate some differences in the height. And then lastly, we use a little bit more like rough terrain by having solid bouldering holes and also soft foam-shaped obstacles as well to provide more of a compliant type of environment as well. And then we show our final results where the OptiState algorithm is shown in blue. Just using the common filter alone is shown in green, the VRO SLAM baseline in magenta, and then the ground truth from the motion capture system in red. We also numerically show our results by looking at the root mean squared error percentage improvement over the VRO SLAM baseline, and we show a 65% improvement using OptiState. Of course, we do need to ask ourselves, how important, for example, is including the common filter as input in terms of the training, and it shows that, without the common filter input, we only can show a 10% improvement. So, having the domain knowledge that seemed to help a lot for training in the GRU. Without including the latent space, we also don't get as high of a percentage improvement. If you just use a common filter alone, we get about -76%. But I do want to include a caveat here in terms of why the common filter did so much worse, and that's really because of the slippery data set. In general, actually, the common filter did quite well, but because if the robot is doing a lot of slipping, then it violates all of the model assumptions that the common filter assumes in terms of the dynamic model. And so this is why it did much more poorly compared to OptiState. Okay, so this concludes really the main portions of my dissertation. Of course, the dissertation includes many other works as well, so I just picked 3 of them to highlight here. But I do want to talk a little bit about my current work as well, and then also the future directions, which will be part of my postdoc that I'll be doing again in Mitsubishi. So first, we were working. So me and Yusuke actually were working on this sort of modification of the scalar robot. Which is, is able to do quadruped locomotion, will show also biped locomotion. I think the original idea of this is that, I don't think we need to directly design robots to look exactly like a human. We see many humanoids nowadays, but I think it's also interesting to have more multimodal morphology where the robot can essentially shift its shape based on a certain task. So this is kind of what inspired us, I think, to develop this kind of multimodal robot. So here I kind of show sort of all the different kind of motion I can do. Maybe I can skip a little bit ahead too. So it's also able, I think now it's going to do like the rolling. So again, it's kind of, it started really as more like a fun project, but I think also from a research perspective, I think it's very interesting just because it's dynamically extremely complicated, especially for biped locomotion, because it's not supposed to be strictly a biped robot. As you can see, the arms are very heavy and much longer relative to the body. And then here we show also some pull-up. So it's, again, capable of doing a lot of different things. And again, in the presentation, I also showed the admittance controller running on this as well. So it's, again, a very cool system to work with. But this also, because of the complexity of the dynamic model, inspired us to also do some reinforcement learning. So here I showed our reinforcement learning algorithm on this robot using the Mojoko simulation. Again, actually using a new version of Mojoko, which is called MJX, which allows parallel environments, so kind of similar to the Isaac Gym concept. So here we show it on rough terrain. Again, it's very difficult to do because, again, before the scaler was really doing all open loops, and now we want to do closed loop with this kind of reinforcement learning algorithm. And then on the right, I kind of show all the things that we consider, like penalizing velocity in the height, penalizing torque. And again, I won't go too much in detail here, but this is one of the things that we were showing. But of course, in simulation, it's actually quite relatively easy to show things working, especially once you get to 300 million time steps and things just tend to work. So now the challenge is, how do we put this on the hardware? So that's something that we're working on right now. Okay, so that's my current work. So now I want to get into the last part of the presentation, which is my future direction. So I want to go a lot deeper into the idea of understanding. And the reason why understanding is typically difficult is because, or understanding for the robust understanding of its environment and what to do, is because long horizon decision making is really difficult without explicitly encoding the instructions for the robot. So that's why, again, my passion for active SLAM is the idea of making completely autonomous behavior for robots. So I think it's important for them to do decision-making also kind of autonomously without maybe explicitly encoding those instructions. And I think this is where vision language models, or VLMs, can come in. So I've been looking much more now into VLMs as well. So I want to present one example of VLMs, which I think is quite impressive. But again, there's a lot of works nowadays trying to use VLM for these kinds of autonomous decision-making. So one of the papers is called MoCA. So the user simply gives a sort of global prompt that might say, clean this table. And then from this global prompt, the VLM will create sort of subtasks for the robot, which includes, finding the graspable part of the image, the functional part of the image, the target part, and then also it generates some waypoints. So what they do is they segment this image and they put some key points using, typical segmentation methods. And then it essentially formulates the problem as a multiple choice question. Again, so the graspable part will be the red point. So that's how it sort of generates it as a multiple choice question. The functional part will be the brush of this object. And then the target will be the center of this piece of trash it's trying to clean. And then it has a pre and post contact, which they call as their waypoints. And then after it selects those waypoints, then the robot essentially activates the motion and then cleans up the table essentially autonomously. Shown kind of like this, like here. Again, so what's impressive here is simply that the user only said clean this table, and all of the rest of it is done essentially autonomously by the robot. And nowadays, a lot of companies are also getting into this. So, for example, Agility Robotics is now using it to essentially try to put the piece of trash in the right bin. Again, the robot didn't know beforehand what is the correct bin. It hasn't been encoded specifically. But through the VLM, it's able to understand that certain objects needs to be in a specific bin. So I'll skip a little bit ahead. So for example, it has this kind of plastic here, and then I'll put it in the correct trash. I guess the brown box will be then in the recycling bin. But again, it didn't know about these different bins, or at least it hasn't been encoded to know about that until the VLM looks at it and then uses it to make its decision making. Okay, so I decided, why don't I just try this myself? Again, this only took about 2 hours to put on the robot. Very simple. So I used GPT for vision. I provided a segmented image. And then I also provide these key points, again, formulating it as a multiple choice question, because ultimately, at least so far, people have shown that VLMs are very good at making sort of multiple choice decision making. So here I show one example.
Selected command to turn left, reasoning. Large brown box directly ahead, path obstructed. Turning left seems clear.
And I also encoded so I can give the voice instruction of what it's going to do beforehand. At least we know already, okay, what kind of decision the robot will do.
Selected command forward. This path directly ahead is clear. No obstacles nearby. Safe to proceed forward.
And yeah, so that's, again, a very simple example, but again, this only took just a couple of hours to set up. And we were able to already show some kind of results. And so that's just one example of using, for example, a VLM. And of course, there's still much more work to be done. So I'll talk about sort of what that work could be. So one of the things I'll be interested in, when I'm doing my postdoc is to go more into the multi-dimensional mapping area. So in terms of, for example, trying to represent a map in terms of voxels, we might have a legged robot with an arm because, those systems can be well suited for mapping, for example, human-made environments, and then also opening a door through its arm. You could technically also use humanoid robots as well. And then we'll have a LLM, and then we will prompt the LLM to say, explore the environment as much as possible and focus on mapping X, Y, and Z, for example. We might also have some sub-prompts, which includes, for example, the robot state, this description of the robot, and also some constraints. And then we have, different kind of sensors we include, for example, RGB cameras, even tactile information to potentially measure the coefficient of friction, which can all be used to build this kind of multi-dimensional map. And then the image can be used as an input to the VLM, and then the VLM can provide all the different object descriptions in the environment, and then send that information back to an LLM. And the goal of the LLM is to essentially choose a motion or the next motion, as you a little bit like I showed in the example previously, to essentially do the task of exploration. I did provide one point here, which is cross-communication, because I'm also interested in, for example, in the cross-communication between these kind of large language models. To give an example, the VLM might see a door in front of the robot, But it really needs to have more information in terms of what to pick for the next motion. For example, is the door open or is it closed? So that's the kind of question that LLM needs to send back. And if it's satisfied with the information, then I can go into the next task. So then that's where I show sort of this motion selection, which is the goal of the LLM. And then I think that a lot of these motion we can pre-train already. So the LLM is sort of choosing a sequence of motions. So those, motion can be either learned through reinforcement learning, behavior cloning, or model-based algorithm. It really depends on which task you're looking for. Again, personally, I believe that, each technique can be valid depending on the task at hand. So this is, again, a very general overview. So, but of course, we can sort of begin segmenting this kind of framework in different kinds of research questions that I'll be asking myself. So from the mapping part, there's the question of how do we best represent such a large global voxel map? And also what information can we extract from it that will be suitable or interpretable by a VLM in the best way? Even on the motion primitive side, I think there's a lot of research possibilities. So each of the, it's actually very easy to train, each single motion individually. But, when you have a sequence of these motions, the transition between one or the other one is not so trivial. So there can be some research in how do you, connect these kinds of motion primitives. And then, of course, there's a lot of questions to be asked on the LLM or VLM side of things. One of them that many people are asking is how do we optimize the prompts to achieve better sort of these high-level directives? So one of the methods people are using is to freeze the weights of these language models and then add an additional layer and train those layers to be more specific to the task at hand. I think it's also very interesting that these LLMs can do some kind of self-coding and analyze data and execute code on that data. So, and then lastly, I think this is the part that I am most interested in is, can we somehow formulate these large language models as a control problem? Because ultimately the safety and also the uncertainty in terms of what it's outputting are going to be a big concern. So I think there can be a lot of contributions in trying to maybe formulate it as a control problem. Again, I assume this is going to be very challenging, but it's something that I want to look more into. So just to give a summary of the contribution of this presentation. So first, we evaluated the feasibility of end-to-end frameworks toward motion planning and state estimation while considering the effect of uncertainty. I showed some auto-calibration techniques for both planners and controllers, for locomotion, also manipulation, wheel-to-sim tasks, which really help tune these kinds of large end-to-end frameworks that I showed in my active SLAM research. And then finally, I demonstrated also the utility of still trying to unify sort of model-based methods and also machine learning techniques. Because again, I think the domain knowledge that we already have can at least, at the very least, help teach those machine learning models much more quickly. So I think there's still, these are sort of valid areas to consider. So now I just provide my list of, the publications that I've done and also patents, peer review awards. So these are some of the journal and conference publications that I did. And then also I was able to do some patents from Mitsubishi. And then I also did a lot of peer review of different papers. And then also I'm very thankful of the sources of funding that I've received for my bachelor degree and then also PhD. And then for the Amazon Science Fellowship Award, I also want to thank my hosts, Arbaz Khan and Bharatian Balaji, who also, had a lot of interesting research discussions. So I'm very thankful for that experience. So now I want to get into the acknowledgements. So I'll try to make it not too long, but there's people I do want to thank because I do plan to send this recording to my friends and so on. So first, I want to thank my parents and my brother. My parents have been very supportive of me in my PhD journey. They rooted me for me the entire time. So in case I pass the defense, this PhD would not just be for me, but really for them. And of course, I want to give my utmost thanks to my PhD advisor, Dr. Dennis Hong. He's an incredibly generous and very honest person. I could have not asked for a better advisor than him, and he gave me unlimited freedom to pursue my passion and allow me the freedom to study really any topic I wish to study. And I think without such freedom, I don't think I would have had the success that I had, but also I wouldn't have enjoyed, I think, this journey in my PhD because, again, as you might have noticed in my work, I like to explore different topics. So I'm very happy that I was able to do that. And I'm also really inspired by his positive outlook on life and how he handles himself in difficult situations, always with calm and with a smile on his face. So I want to strive each day to have that kind of same mindset. And of course, I want to thank my committee members, Professor Santos, Professor Jawed, and Professor Soado. They've given me a lot of valuable feedback on research, and the classes also inspired me as well. Professor Santos for showing me the ways of control for the first time. I really loved her class a lot. It made me fall in love with controls. So it's obviously a topic that's all over my dissertation because of that. I'm also really thankful for her support and recommendations to some of the programs I applied. So I really appreciate that. And then Professor Jawed for introducing me for the first time on soft robotics. Again, I really believe soft robotics is going to impact, really the field as a whole, especially since we care more about, robots falling. How do we not damage the equipment and so on? So I think that will be sort of the natural evolution of these robotic systems. And then, of course, Professor Soado, who challenged me to think deeply about what I'm working on and also keep in mind the impact my work will have in the future. He's also the reason why I'm looking more into the LLM and VLM side of things. And again, I'm very fascinated in this topic because of really thanks to him. And of course, I'm also incredibly grateful for his help and contribution in several of my research works as well. So I want to, of course, give thanks to the members of Mitsubishi Electric Research Laboratories. So as Dr. Hong introduced at the beginning, I'll be doing my postdoc there. Actually, I also did 2 internships there previously. So of course, I'm very grateful for the opportunity they gave me. So I want to thank my host, Marcel Menner. He actually taught me a lot about the auto-tuning techniques. And so of course, the auto-tuning had a big impact in my dissertation. So I'm extremely thankful for his guidance on that. And then I want to thank my boss, who's Stefano. He's the one who ultimately offered me the job. So I'm very thankful for him entrusting me to do a good job at the company. And I want to make him and the team proud once I'm there. And then, of course, I want to thank Savis. He's not only one of the best co-authors I had, but I appreciate our deep research discussions. He's also become one of my best friends. So I feel really grateful to have such a friend who's not only loyal, but really supports and wants to see me do well. Again, these friendships, I think, are very rare in life. So I did want to say this to him. Now I want to give thanks to the Scalar team. So they gave me a home at Romella to thrive and feel welcome in. I want to thank Yusuke Tanaka for his kind support in helping me with so many of my research papers. He's one of the most talented people I know, capable of both hardware and software. I mean, I think there's a reason why so many people in the lab, including myself, would often go to him for questions and advice. He was always ready and happy to help without expecting anything in return. And lastly, I feel really grateful that we were able to go to so many conferences together. We had a lot of good times in Hawaii, Austin, and also Japan, and it's something I will forever cherish. I want to thank Yuki Shirai. He was the one who introduced me to the Scalar team and also helped introduce me to important topics in robotics, which was incredibly helpful as I transitioned from bioengineering to mechanical engineering. And then throughout my PhD studies, we had a lot of great moments together in areas involving research, but also from our social interaction. We both actually did internships at Merle together, and also we also got jobs at Merle. So it's kind of a very nice and fortunate coincidence. So again, I feel very grateful to have shared so many memories with him, and also very thankful for the opportunity to create many new memories soon. I want to thank Shen for his wisdom and knowledge in legged robots. I'm particularly thankful for our discussion in force control. This helped me publish a work in this domain, so specifically the admittance control paper. I want to thank Feng and also Alvin, who contributed actually already a lot to the Scalar team. And Alvin is one of the most talented undergrads I've seen, so I'm really excited to know what he will do in the future, and I think he'll go really far in life. And then I want to thank, of course, all Romella members, with special thanks to Josh. He was one of the first people I met at Romella and was the first person to help me implement my algorithm in hardware for the first time. So he was one of the few willing to actually help me at a time when I really needed it the most. And then I want to thank Jeff. We had a lot of enjoyable late night discussion, and I'm also grateful for him giving us a tour at Boston Dynamics. That really just inspired me to continue working in this field. And then finally, I want to thank all my family members I have in Austria. I would be the first in my family with a PhD, so it's a kind of a big deal for us. So I feel really honored that they've been sending me many messages and rooting for me. So I'm very thankful for that. Lastly, I want to end by saying that this PhD journey has been really wonderful, filled with many ups and downs. Coding to 5 a.m. We brought the whole wall to Kyoto, and then the wall got stuck in the door, and then we had to disassemble and do all these crazy things. But we always made it work in the end. We also had a lot of fun in the process. And then with many successes, like the one we had at ICRA with the robot going over slides, climbing. But of course, we also had many failures as well, and then that we can also learn from. But yeah, I just want to thank Ramel as a whole and for all the memories I got. So that's the end of my presentation.